So now we're going to get into how to actually write down the electronic configuration for pretty much any atom. Now, in order for us to do this, first we have to establish the order of the subshell energies, because according to the rules that we just covered in the previous video, we have to start from the lowest orbital first in terms of energy when we're assigning electrons, and then we just simply continue to add electrons, as you're going to see in a couple of examples that we're going to look at. So what you're looking at here on the screen, on this slide right here, is a diagram that is used to help us to remember the order of the orbitals in terms of their energy, right? It turns out that for multi-electron atoms, it's not a simple case of the first shell containing the 1s orbital, and then the next shell containing the 2s, and then the next shell containing the 3s, 3p, and 3d, and so on. It turns out that at a certain level, as you go higher in energy, there's some overlap between the shells, and therefore the higher orbitals of certain shells will have more greater energy than the lower orbitals of higher shells, all right? So as a result, this diagram was put together in order to help to memorize the order of orbitals. And I remember when I was a student, the way I remember or memorize this diagram is that I'll take a sheet of paper and I'd write down 1s, 2s, 3s, all the way down to 7s on the left side. And then I'll start here where 2s is for the second shell and start writing down 2p, 3p, 4p, all the way down to 7p. And then I'll start at the 3s for the third shell. And over here, I'd start with 3d, 4d, 5d, 6d. And then for the fourth shell, I'll start here, 4f, 5f, and that's it. All right? So the next thing I would do is draw the arrows as you see indicated here. And basically, you'll get the order of the orbitals or order of the subshells by simply starting from the top arrow, starting from the tail of the arrow to the head. So that would be the first orbital in terms of energy. And then the next in line would be 2s. And then the next in line would be 2p, 3s. And then the next in line would be 3p, 4s. And basically that's it. And that's how you get the orders, as you can see listed here. All right. So that would represent the order of the orbitals or the subshells in terms of their energies, right? So let's look at how we actually determine the electron configuration of the atom. So the principle that is used to do this is called the Auf Bau principle, right? And basically, if I'm not mistaken, Auf Bau is a German term which means building up, all right? So basically, it's the hypothetical approach of building up the atom in terms of the electron arrangement as you go from one element to the next of higher atomic number, all right? So let's start off with the simplest element, which of course is hydrogen, which has an atomic number of 1, and the 1 electron will therefore go into the lowest energy orbital, which would be the 1s sublevel, right? So therefore the electronic configuration of hydrogen would simply be 1s1. Then the next element would be helium. The atomic number of helium is 2. So to get from hydrogen to helium, all we have to do is add an electron. Now we know that the s sublevel can contain at most 2 electrons, so therefore we can simply place the other electron in the 1s sublevel, and therefore the electron configuration of helium is 1s2. And then the next element would be lithium. So lithium, of course, has an atomic number of 3. So therefore, to get from helium to lithium, we simply add an electron to the electron configuration of helium. But we now know that the sublevel for helium is filled, for the 1s sublevel that is. So therefore, that means that the other electron, the third electron that is added, will have no other option but go into the next shell, and specifically go into the lowest energy orbital of the second shell, which would be the 2s orbital. So therefore, the electron configuration of lithium is going to be 1s2, 2s1, all right? And so on and so forth. So if I were to write down the electronic configuration of the next element, which is beryllium, which has an atomic number of 4, then the electron configuration of beryllium will be 1s2, 2s2, all right? And then if I were to do the same thing for boron, which has an atomic number of 5, then, so boron is 5, the electron configuration will be 1s2, 2s2, and then the next electron will go into the next higher sublevel, which would be the 2p sublevel. So the electron configuration of boron of the 2p1, all right? And so on and so forth, right? So that's basically how that is done. Now, as you can imagine, when you get to heavier elements or larger atoms, the electron configuration can be very long, right? So if you get to something like calcium or uranium, etc., right? Those larger atoms where the atomic number is relatively large, then of course electron configuration would be a long string of these symbols, right? So it is easier to basically summarize the electron configuration into a more abbreviated form for most purposes, right? And the way we do that is that we replace the portion that corresponds to the electron configuration of a noble gas with a bracketed symbol for that noble gas. So let me use the lithium example, right? So this here, we just did the full electron configuration of lithium, 1s2, 2s1, right? So the abbreviated version is that we look for the group 8 element that precedes lithium in the periodic table. And that element would be helium, right? And if you look at helium, which is actually right here, helium has this electronic configuration, 1s2. So basically, to write down the abbreviated version of helium, we simply put, not abbreviated version of helium, the abbreviated version of lithium, we simply replace the 1s2 part of lithium with the symbol of helium in square parentheses, and then we simply write down beside that what remains outside of that, and therefore this would be the abbreviated electron configuration of lithium, all right? Now, it might not look abbreviated, this configuration here, compared to the full configuration shown here, but it does make a difference if you look at a larger atom such as titanium, all right? So if I were to write down the full electron configuration of titanium, let me do that here. So for titanium, the atomic number is 22, right? So for titanium, the electron configuration would be, the full electron configuration that is, would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, all right? So that would be the full electronic configuration of titanium, right? Now, as I said before, in order to get from the full electron configuration of titanium, so this is for titanium, right? What I would do is look for the group 8 element that precedes titanium. So if I go to the periodic table, you'll see that the group 8 element that precedes titanium is argon. And the electron configuration of argon would be the same as this part right here, right? So this part here is basically the same thing as the electron configuration of argon. So basically what I would do to get the abbreviated version is replace this part with the symbol for argon in parentheses, and then write down the rest that remains after that, which would be the 4s2, 3d2. And therefore that would be the abbreviated version. So as you can see, obviously, there's a big difference between the abbreviated version and the full electron configuration of titanium, all right? The string of symbols here is much longer compared to that of the abbreviated version. Okay, all right, so that's basically how that is done. Okay, so let's look at this example. This question says, write the electron configuration for sulfur using both the SPDF and the orbital diagram. So the first thing I would do, of course, is look up the electronic configuration of sulfur, and you'll see that it is 16. Let me use the black ink. I prefer black ink. Okay, so let me do the SPDF notation first. So that would be 1s2, 2s2, 2p6, so that's 10 so far, then 3s2, and then 3p4, and that should give you 16 electrons, all right? So this would be the SPDF notation. Now, as far as the orbital diagram is concerned, remember the orbital diagram uses boxes to represent the orbitals. So this would be the 1s orbital, which would contain 2 electrons, and both electrons will be spinning in opposite directions. And then the same is true for the electrons in the 2s orbital, spinning in opposite directions. And then in the case of the 2p orbitals, remember now there are 3 p orbitals in this 3 orbitals in the p sublevel. So we have 6 electrons distributed among them. So that would be 1, 2, 3, 4, 5, and 6. All right. And then we get to the 3s sublevel. Again, there are 2 electrons here spinning in opposite directions. So this is 2s, this is 2p, and this is 3s. And then we get to the 3p sublevel. Again, there are 3 orbitals in the p sublevel. And in this case, there are 4 electrons to be distributed. So it would be 1, 2, 3, and then we start pairing them up, 4. And that would be the 3p sublevel. So that would be the orbital diagram representation of the electron configuration of sulfur. All right? Okay, so as a consequence of what we just discussed, how the electrons are added to atoms going from one atom to the next across a period to get the electron configuration, you're going to find that there are certain regions in the periodic table where these elements are located, which are designated certain blocks, right? So what you're looking at here on this slide is basically the periodic table with different regions colored, right? The blue regions here are said to be, the elements belonging in those regions are said to be the main group elements, and then the transition elements would occupy the region which is colored pink, and then the region which is colored, I think this is yellow, those elements are called the inner transition elements, all right? So the reason why we have those categories is because of what we observe when we add electrons to the atoms and the resulting electron configuration that that we find. So, sorry about that. So basically, as far as the main group region is concerned, if you look at this region here, right, as you go from one element to the next, right, you're adding an electron to an s orbital. So in this case, it's 1s, in this case, it's 2s, 3s, and so on, right? So we call this region here the s block elements, right? Now over here, so that is part of the main group region. Another part of the main group region is where we call this region here the 2p sublevel, or the p block, I should say. So what that means is that as you go from one atom to the next, adding an electron, you're adding an electron to a p sublevel, right? So for example, in the second period, we're adding an electron from here to here to here to a 2p sublevel. For down here would be 3p sublevel, where you're adding an electron, and so on and so forth, right? And then we get to what we call the transition element region. It's also known as a D block region. We call it as such because as you go from one atom to the next, when you're adding an electron, you're adding an electron to a D sublevel, all right? And then finally down here, where we have the inner transition element, it's also called the F block region. And again, that's because going from one element to the next across a period, you're adding an electron to an F orbital, all right, or an F sublevel. Okay, so that's basically how we arrive at the names for these different regions. It's as a result of the electron configuration that is obtained when you add an electron to the atom as you go from one element to the next across that particular region. Okay, so what shall we talk about next? Okay, so another example here. The question says, give the complete ground state configuration of the strontium atom. And it's asking for the SPDF notation and the abbreviated version. So strontium, let me look up the atomic number of strontium. The atomic number of strontium is 38. So let me write down the symbol here. For strontium, it's 38, all right? So basically what you'd have to do now, and what I have to do, is referred to the diagram which gives the order of the orbitals in terms of their energy. So if you do that, then the first thing you'll write down here is that for the first shell, it's the 1s orbital, 2 electrons will go there. Then you're going to have 2 going into the 2s orbital. And then for the 2p sublevel, there will be 6. For the 3s sublevel, there will be 2. For the 3p sublevel, there will be 6. For the 4s sublevel, there will be 2. And for the 3d sublevel, well, let me see how much we have so far. So up to here would be 20. So for the 3d sublevel, that would be 10, right? So that's 30. And then the next sublevel after 3d is 4p, and that would be 6. And then the next sublevel after the 4p is 5s, and that would be 2, all right? And that gives you the grand total of 38 electrons, right? So that's just checking. That's 20 plus 10, that's 30 plus 6, that's 36 plus 2, 38. Okay, good. So this would be the full electronic configuration. Now the noble gas configuration is where we identify the group 8 element that precedes strontium. So the group 8 element that precedes strontium, if you were to look at that, that would be krypton. And the electronic configuration of krypton would be all of this here up to the 4p6, right? So that would be the electronic configuration of krypton. So therefore, the abbreviated electron configuration of strontium would be krypton, the symbol, Kr in square parentheses, and then 5s2. And that would be the abbreviated version, all right? Okay, so we're going to stop this video here. And the next topic we're going to discuss are a couple of exceptions to what we were just discussing in terms of the Auf Bau principle, all right? Okay, until then.